All right, hello, boa tarde. Thanks for sticking around for the last talk of the day. I'm a research ecologist at the University of California, Davis, and I'm going to talk about our project, the Open Forest Observatory, to facilitate forest mapping at the individual tree level using drones. So the OFO is a collaboration across a few universities and other partners with three main objectives. The first is developing open source tools to facilitate producing forest maps from drone imagery. The second is producing a public open database of drone-derived imagery and associated forest maps. And then third, and just as important, is a public database of ground reference data, like traditional forest inventory data with geospatial tree locations for training and validating the drone-based mapping methods. And this project really aims to allow groups and individuals to perform drone-based forest mapping regardless of their sort of level of technical expertise or budget as well. Even drones these days, all of these methods work with low-cost consumer drones, and we really aim to bring the state-of-the-art algorithms into a sort of simple, user-friendly interface. So you might be asking, why drones, especially when we have this wealth of Earth observation, satellite data, and like here's a great example, the WorldView 3 super high resolution, 50 centimeter imagery. I think Planet has similar resolution in some of their satellites. And indeed, this sort of imagery has been the basis for some individual tree detection work, like this project in the African Sahel, where they had pretty good accuracy in individual tree detection, but these methods tend to break down when forests get any denser. This is a pretty sparse, more like a savanna system, and in denser forests, satellite-based methods, even using these super high-resolution satellites, tend to focus more on these broad-scale metrics like carbon and biomass, or in this case, this Facebook research work to produce a canopy height model. So even the highest resolution satellite imagery has limitations in the context of individual tree mapping. And then in comparison, though, drone imagery is much higher resolution and really enables some really powerful approaches to individual tree detection and mapping. And in addition, it's so I guess you can collect it at any time, essentially, and for relatively low cost. The general approach to forest mapping by drone involves flying the drone in this series of contiguous transects, this sort of serpentine or lawnmower pattern, collecting images in this dense grid of images, so that you have a lot of overlap from one image to the next, like even up to 90% overlap. So any given tree will show up in multiple images from different angles. And then you can stitch those images together into a top-down orthomosaic. This is a geospatial data product because every pixel here has geospatial coordinates. It's a map. And because we get views of every tree from many angles, we can apply principles of like perspective and triangulation to actually estimate a 3D model of the scene. This is a process referred to as photogrammetry or structure from motion. And so in addition to the nice imagery, we get a 3D model. And so this is a canopy height model where the lighter colors indicate taller surfaces. And then this can be the basis for some tree detection algorithms. For example, like a local maximum detection could find the treetops. And then this can then sort of be the basis of the data that is used for like forest forest management, conservation planning, ecological research when you have these sort of discrete tree data. And then also, so I showed the canopy height model as a form of representation of the 3D data. Some people would say that's more technically a 2.5D model because it doesn't show like the undercuts under the tree crowns. But we actually do also get a full 3D model. This is an example of, this is a mesh model that we got through the same photogrammetry run from the same site. We also get point clouds. And so when you set out to map a forest by drone, there's basically an infinite array of decisions to make from how you collect the imagery, like the drone flight altitude, the camera angle, and then how you process the imagery through the photogrammetry algorithm, then how you take those products and detect trees from them. And these are all decisions that we spent a lot of time in the Open Forest Observatory evaluating the sensitivity of the results to these decisions in these sort of factorial combinations. Our approach is generally to do data collection and processing with different sets of values for these different parameters, end up with a tree map, and then we can evaluate the accuracy against reference data. And so here's an example. I'll get into the details of exactly how we do this, but this is showing comparing a set of drone mapped trees to a set of reference trees from a ground-based survey. And so when we do this in the systems where we work is mostly western United States conifer forests. We get tree detection, recall, and precision in around the 0.7 to 0.9 range. We actually think we can improve this quite a bit with some methods I'll describe that we're working on. And then tree height estimation by drone gets R squared of around 0.95. And so we published those results and sort of the like recommended workflow in an academic journal, but then maybe more relevantly, we also published this as a public sort of guide for the general audience on that we hope will help people collect imagery in a way that will be most useful for forest mapping. Okay, so now with that sort of background on some of the main considerations in mapping forests by drone, I'm going to take you on a lightning tour of some of the tools we're developing to help streamline this process. And just kind of broad context, this is all very much a work in development, a work in progress. These tools are all in varying stages of development with the kind of development maturity roughly indicated by the color of the bullets here, but we'd be really thrilled to collaborate with anyone interested in contributing to the development of any of these tools, and even just interested in using the tools. We're happy to support people using them. They're all usable to some extent already. Some have some rough edges still, but they are usable. So let's say you went and collected drone imagery from a dozen sites, and the first step then is to process it with photogrammetry into the geospatial data products. That's what our first tool here to automate photogrammetry comes in. Without any sort of automation, if you're just using like a photogrammetry software directly, if it's a GUI, it's a lot of point and click to start one processing step, and then you have to wait till it's done. Might be the next day, then point and click some more, and then repeat that all over for the next data set, and it's very cumbersome. And there are like command line options, but they also, you have to construct this big command line call with all these parameter values and keep track of it all. And so to facilitate this process, we wrote this Python library that it actually doesn't require knowing any Python. The way it works is you prepare a config text file in YAML format that specifies all of the processing parameters, and then just with a single command line call, you reference that config file, and then it runs the workflow from start to end with those parameters, with the config file then remaining as a sort of documentation of the run for reproducibility. And we provide a example config file that's pre-populated with the configuration that we've found works best in the forests we work in, but it can easily be customized. It's a little grainy up there, but it's on GitHub. It's called Automate Metashape. And that actually leads me to my most embarrassing admission here at FOSS4G is that currently this just supports one photogrammetry backend that's actually a commercial software called Metashape, but it's actually at the very top of our to-do list over the next few months to extend this to some really promising open source tools for photogrammetry like Open Drone Map and Call Map. And the idea is that this, from the user's perspective, this would be a back-end agnostic tool where you still write the config file, but you have one more parameter, which is which back-end photogrammetry engine you want to use. Okay, so let's say now you've processed all your imagery, you have your geospatial data products. The next step might be tree detection to make a tree map. And the most straightforward approach to that is to use like geometric methods like the 3D model, like I mentioned, like detecting local maxima, calling those your treetops, and then assessing the accuracy of those tree detections. So both of these steps are implemented in an R package for the Open Forest Observatory that's in development, because ecologists actually generally are far more comfortable with R than Python, myself included, actually. So the tree detection algorithm that we're implementing is currently it's called a variable radius local maximum filter. This is what has been found to work well in many contexts, where to query whether a pixel is a treetop, you search within a certain radius around it and ask, is there anything taller in this radius? And if not, then we say that focal pixel is a treetop. And work has shown that we get generally most accurate results if we have that search window vary in proportion to the height of the focal pixel, like you can kind of see illustrated with these two green circles here. And so this algorithm is actually already implemented in this fantastic R package called LiDAR. And so we just basically provide a wrapper around it that will have default parameters for this variable radius function tailored to specific forest types, and then a slightly more straightforward interface to where you provide your canopy height model to get the treetops. So it's sort of a trivial contribution, but a much more substantial contribution that we're developing is then for the next step of evaluating the accuracy. So first thing you have to do if you have two tree maps, you have to spatially co-register them because they might not have they might not both have like absolute global accuracy. We assume they have sufficiently accurate like relative accuracy, but we still have to like co-register those two data sets. So we have functions for aligning two tree maps based on the kind of constellation of trees in the maps. And then the next step is to identify pairs between the field ground reference trees and the drone detected trees, so that then we can ask, was this drone detected tree a true positive or a false positive, and then quantify our recall and precision. And those are also implemented in our package. And then we'll be adding more functionality like tools to access the OFO data, which I'll describe at the end. So I talked about the kind of most straightforward like geometric approaches to tree detection. I actually think there's a lot more promise in using computer vision for tree detection, especially with our super high resolution imagery. And there actually are already some great packages, pre-trained computer vision models for tree detection like Deep Forest and Detect Tree 2. And then Meta's Segment Anything model, SAM2, is not specifically pre-trained for trees, but it actually it works quite well, basically right out of the box for this. The challenge with computer vision models, though, is they don't deal like natively with geospatial data. Like our ortho mosaics could be huge and have kind of amorphous boundaries. The computer vision models expect these very rigid, uniform tiles, square images, usually like 512 pixels by 512 pixels. And so what you have to do is chop up, or a lot of people say chip up the big image into these little chips that can then be fed into the computer vision model. Then you get the predictions out of it. You have to reassemble those back into the full map, remove duplicates if there were overlapping tiles, and then reassign the coordinate reference system. And so those pre and post-processing tasks are implemented to some extent and in different ways in different packages, but not in a very complete or standardized way. So we're working on what we call the tree detection framework to take care of that pre-processing and post-processing. And so another case where we want to make it, from the user's perspective, agnostic to your back-end computer vision model, and you just specify how big your tiles should be, and it takes care of shipping it, feeding them into the model, and then reassembling the predictions at the end. Okay, so I've been talking all about tree detection, but another critical part of forest mapping is species classification. Species can matter for forest management, like special treatment for rare species or invasive weedy species. So we also have some work we're doing. So with our really high resolution imagery, this also is a great case for applying computer vision for species ID. And the challenge, though, is that these top-down perspective doesn't really give you all the detail that you might want for classifying tree species. But it turns out, if we go back to our raw drone imagery, even a camera that's pointed straight down gets oblique views at the edges of the frame. And then we actually also intentionally fly lower altitude oblique missions to intentionally get side views. And so these are the same 4 trees from 2 different views. And you can see that you get more detail. If you were trying to ID this tree, that oblique view is probably going to be more useful. And we don't get just 2 views, we get, generally dozens of views of every tree from all of the different photos it appears in. So this can really help to increase the robustness of the computer vision classification. The challenge, though, is translating between the raw drone image and the geospatial coordinates. The pixels in the drone image are not spatial. They're just pixel X and Y coordinates. But we really want this data in a geospatial format. So we can take advantage of the fact that if you know the exact position of the drone camera when the image was taken, and then also the parameters of the camera lens, you can actually project a ray through any pixel in the image into geospatial coordinates. And so we have developed this package, a Python package geographer, to enable geospatial predictions from raw drone images using this concept of these rays projections. And this leans really heavily on algorithms from computer graphics, which is all about taking a 3D model and rendering it to a 2D view. So we really lean on some computer graphics packages for this. And so the workflow is if you have a map of trees that you mapped in the field, you've assigned species, you can use geographer to then render those labels onto the raw drone images. So we get these training masks, which is what you might get traditionally by hand, kind of manually annotating images and inspecting and saying, this looks like a ponderosa pine, and labeling it. But these labels actually came from field data, ground-based forest inventory data, and in an automated way, we can render those labels onto all of the drone images. Could be thousands of images from a drone flight. And so then we can feed these to fine-tune a computer vision model to predict tree species. Then at a new site where we want to use the model to infer species, we can ask it to predict species. And then using the same algorithm in reverse, project those labels onto the geospatial coordinates. And in some experiments, we've found that using these multi-view images, raw drone images, increases accuracy quite a bit over the kind of standard of just using the top-down orthomosaic view. Okay, in the interest of time, I'm just going to gloss over this last one, but this is applying these same multi-view tree detection concepts to multi-view classification concepts, but to tree detection. So rather than using the orthomosaic, we can actually use the oblique imagery to detect trees that might not be visible from overhead. Let's get through that. And then just so that I have time to mention our last, but equally important effort of producing public data. And so here's our current state of our drone data catalog. It's unfortunately fully focused on the Western United States right now where we're based, but we would love for this to become a global catalog, and we welcome contributions. We do have a web-based catalog where you can browse the imagery and download full data sets. We want to create a stack catalog to reference all of this, and so it can be searched in standard ways. But we have hundreds of drone imagery acquisitions from forests across this region. And then just as or maybe even, just as importantly, at most of these sites, that's where we have the drone imagery, we also have detailed ground reference data from traditional ground-based inventories, which we use for training and validating the models. These are available to browse as interactive web maps and then download as well. And we'd be thrilled to add more ground reference data to this catalog as well. Okay, I think I'm about at time, and so I just want to, I'm really presenting on behalf of over a dozen people who have really contributed substantially to all of this work, all of the tools and data resources I described. I want to acknowledge funding from the U.S. National Science Foundation and the Nature Conservancy and CAL FIRE, and thanks for coming. Obrigado.